Welcome to this engineering masterclass. In this video, we will explore capture technologies and basics, deconstructing post-combustion, pre-combustion, and oxy-fuel archetypes, as well as thermodynamic separations and industrial reboiler duty equations. We begin with Part 1, focusing on the primary capture archetypes used in industrial applications. Post-combustion capture intercepts carbon dioxide after fuel combustion in furnaces or boilers. It is a favored method for existing power stations due to its high adaptability. However, because flue gas is highly diluted, high-performance chemical solvents are required. Amine solvent mechanics serve as the benchmark for this process. It involves an absorption tower for capture, a desorber to release pure CO2, and continuous recirculation of the solvent in a closed process loop. Pre-combustion capture involves gasification of hydrocarbon fuel, a water-gas shift reaction to increase carbon concentration, and the use of physical solvents at high pressure to dissolve CO2 efficiently. Oxy-fuel combustion uses pure oxygen instead of air. This prevents nitrogen from entering the process, resulting in a highly concentrated flue gas that yields high-purity CO2 through simple condensation. This table compares the three archetypes. You can see the differences in CO2 concentration, pressure profiles, capital costs, and the types of solvent interactions involved. Moving to Part 2, we examine the various separation mechanisms used in these systems. Gas absorption dynamics are split between chemical and physical methods. Chemical absorption uses affinity to overcome dilution, requiring thermal energy for regeneration. Physical absorption relies on pressure, as dictated by Henry's law. Solid adsorption utilizes materials like zeolites, silicas, and metal organic frameworks to capture carbon dioxide. These systems typically use temperature or pressure swing cycles for regeneration. Membrane technology is another key approach. Polymer membranes use solution diffusion, while facilitated transport incorporates specialized carriers to boost selectivity for dilute streams. Cryogenic distillation operates at temperatures as low as -120 degrees Celsius. This phase change process avoids solvents entirely, making it ideal for ultra-pure liquid CO2 production. Part 3 covers the essential thermodynamics and the chemistry of the solvents we use. Monoethanolamine, or MEA, is the standard solvent. It forms stable carbamates at lower temperatures, which are then broken down by applying heat in the reboiler to release the captured gas. Finally, we consider alternative solvents. Sterically hindered amines, such as AMP, reduce thermal energy demand, while carbonate systems offer high stability and low toxicity for specific pressurized applications. Moving on to Part 4, we'll perform an analysis of the energy penalty associated with these capture processes. Capture systems often impose a significant parasitic load. Operating a solvent plant requires diverting steam from the turbine cycle. Combined with power for blowers and pumps, this can cause a 30% thermal energy penalty, leading to a notable drop in net generator efficiency. Reboiler duty is calculated as the sum of three thermodynamic components: the heat of reaction to break amine CO2 bonds, the sensible heat to raise solvent temperature, and the heat of vaporization to generate steam for stripping. Integrating these systems drives up the levelized cost of energy substantially. Reducing solvent reboiler duties is a primary target for current chemical engineering research and development. In Part 5, we examine advanced and modular capture systems designed to improve efficiency and reduce installation complexity. Modular capture units offer a plug-and-play approach. By using prefabricated, containerized modules, industrial sites can reduce construction time, scale capacity by adding units in parallel, and lower overall project risk. Industrial retrofitting is often restricted by footprint. To integrate carbon capture into congested existing plants, engineers rely on process intensification, such as rotating packed beds, to maximize contact area in small spaces. The engineering design process includes several phases: defining the flue profile, performing thermodynamic simulations, designing integration networks, and finally, commissioning to validate performance and long-term health monitors. Key challenges remain, particularly solvent degradation and water usage. Amine degradation from flue impurities requires reclaimers and filtration, while efficient heat exchanger networks are essential to manage high water consumption. This concludes our presentation on capture technologies. Thank you for participating in this module. For further collaboration, research proposals, or technical training, please connect with Dr. M. Fahed Qureshi via the contact details shown here.